Okay, thank you. Can you hear me? Yeah, see that good. So I guess that many people about you have already used well, crypto library to secure some piece of code. And here in this talk, I'm just gonna to ask a very simple question: Is are crypto APIs really usable when you think about security? Um, and this does not work. Uh, this works. So, first of all, I just would like to expose my motivations to have such a talk. Um, Basically, there is very few people on that planet that are really competent in cryptography and at the same time competent in writing secure code. I know one, which is who is DGB, who wrote the Qmail mail server and who is a very competent cryptographer. Maybe there are another one or two other ones, but this is a mix of skills which is very difficult to find here. Yet, many people use crypto libraries on a daily basis. And most of the time, I think that the result is brings unexpectedly low security level cryptographic strengths. And I just would like to expose my thoughts about that. Uh, if you are still not convinced and you think that as soon as you are using crypto, then you are safe. About 3, 4 years ago, some guys from Carnegie Mellon University and the University of Santa Barbara just made an empirical study on the quality of cryptographic code used in Android applications. Okay, so the result was terrible. They just wrote a program, a kind of cryptolint program that automatically check the Java application that they found on Google Play, and then found that about 90% of the application they investigated made at least one mistake. So you could say, okay, that's good for the 10 remaining percent, but still, just have a look at what they checked for. Actually, they just checked for 6 different security or cryptographic problems. Do not use ECB mode for encryption, which looks like to be pretty normal. Do not use a non-random IV for CBC. Do not use hard-coded constant encryption keys. Do not use constant salts when you are using password-based encryption. Do not use too few iterations for password-based encryption. And do not use static seeds for seeding a secure pseudo-random number generator. So that's only 6 very common problems that you can find in cryptographic implementations, and 90% of the Android application would just file these 6 very simple rules. So you can imagine if you look a bit more deeply into cryptographic code, what you can expect. So this talk is not about blaming anybody. Not blaming arrogant cryptographers that do not care about implementations, about programming, about software development issues. Usually, arrogant cryptographers just write papers. They invent new cryptographic protocols. They write a lot of math. They invent security models. They give proofs, and they are still pretty useful. Even if it's not sufficient to have real strong crypto in practice. It's not about trashing ignorant crypto libraries developers, so developers of OpenSSL, developers of Botan, of the Java crypto architecture, crypto API, that do not know everything about crypto and that do not follow the day-to-day happening in the crypto community. It's not about the idiot users of the crypto libraries that do horrible mistakes all the time, most of the time, not all the time. And it's not about the other security aspects of crypto libraries. So I won't speak about side channel attacks. I won't speak about white box adversaries like tampering at the cryptographic code with respect to resistance to reverse engineering, malicious reverse engineering, and etc. This is put aside for this talk. So my goal here is really to expose what I think is a real world problem that has consequences every day. The lack of security related usability in most cryptographic libraries. And I would like just to show you some samples of good practices, because there are some good practices and a lot of bad practices as well that you can find in very common crypto libraries. And at the end, if you have a bit more information about selecting a crypto library, then I will have won my game. And I will also try to sketch usability requirements on crypto libraries, that how should be written the perfect crypto library that does not exist for the moment, but to which requirement we should converge in the future. Okay, so I'm going to speak about mainly about let's say four orthogonal dimensions of crypto security. First of all, I will speak about the security model. So in what are you looking for security when you implement cryptography? Then we will speak about security parameters, mainly key lengths. We could also speak about block length or such parameters. Then I will speak about the choice of cryptographic primitives, and we will see that you can do. It's very easy to make mistakes with that matter. And last but not least, because to have a proper cryptographic or proper application secured with cryptography, you will need to have a good security model, to have a good choice of security parameters, and to have a good choice of primitives, and then you code. But while operating your crypto, you will need also to have good cryptographic parameters, meaning mainly generation of keys, of IVs, of nonces, and we will have a look at that. So let's go to the security models. So if you look at the crypto theory, and it is maybe not so likely that you will have a look at this in cryptographic lectures, because most of the time it will be in advanced cryptographic lectures. And if you just take the case of symmetric key encryption, so I have a symmetric key and would like to encrypt some data. Already, theoreticians of crypto have developed a lot of security models, of formal mathematical security model. You can speak about indistinguishability under chosen plaintext attack or under chosen ciphertext attacks. You can speak about or discuss about the integrity of plaintext or the integrity of ciphertext. You can discuss about non-malleability under chosen plaintext attacks or chosen ciphertext attacks. And there are other ones, taking, for instance, account an adversary that can manipulate keys in the related key settings, etc., etc., etc. So which one to choose? Maybe you can dive into the cryptographic papers and read the theory and the maths, and it's pretty complicated. It's not very convenient for developers to read crypto papers, and I can understand this. There are complicated implications between those security models. So for instance, you can prove security equivalencies, but this is a new term, very complicated. So just take a step back and have a look at three different possibilities to do symmetric encryption. I will here speak about symmetric authenticated encryption, meaning that we will address the confidentiality issue, but also the integrity and authentication issue. And basically, you have three possibilities. We will assume here that you have a secure encryption scheme that brings confidentiality. We have a secure authentication scheme, like a MAC, and we would like to combine them to have something secure at the end. So the first possibility is to have a encrypt and MAC approach, meaning here you are just going to encrypt the plain text, and you will apply the MAC, an HMAC SHA-2, for instance, on the plain text, and then, so here, by the way, this is a Wikipedia picture, and I don't like it because okay, the terminology is not that right, and it shows that you are going to use the same key for both goals, encryption and authentication, which is not a good cryptographic practice. So anyway, and what you will do is just to concatenate the ciphertext and the tag, and this is one possible approach. So the theoretician says that even if you have a secure encryption scheme and even if you have a secure authentication scheme, we cannot prove generically that the composition of two will be secure. So just forget about it. This is not something that you will have to use. The second possibility is MAC then encrypt. So what you will do, and this is typically the strategy which has been chosen by TLS, and actually it triggers a lot of problems with the implementations. So here you will just MAC the plain text, concatenate the plain text with the MAC, and encrypt everything. Okay, so it means that you will have to decrypt before being able to check the MAC. So a new time, the theoreticians here are saying that in certain circumstances, in certain weak security circumstances, it is secure, but we have cases what is not secure, so don't use this approach. And eventually, you have the encrypt then MAC. So here is just, the goal is just to encrypt the plain text and apply a MAC on the ciphertext this time, not on the plain text. And this is currently the only composition that we know that is generically secure. If you have secure encryption and secure MAC, you can combine them and to have security in both cases. In all the cases. So it means that basically there is a single way to do things well, which is encrypt then MAC. And you can have a look at a lot of cryptographic standards and protocols. Not so many protocols are using this approach. And for instance, in TLS, we are paying the price now because when you have to secure a TLS implementation, for instance, against Oracle attacks, it's not very easy. So in real life, first of all, you will never have a passive adversary that is just eavesdropping. There is only passive adversaries which are in the books. You will have to consider active adversaries that can manipulate the ciphertext. And the only viable symmetric encryption model is authenticated encryption. So it means that either you can use a dedicated primitive like AES GCM, for instance, which does both jobs at the same time and which was designed for that, or you can use an encrypt then authenticate scheme using, for instance, AES encounter mode and hashMAC SHA-2 plus key derivation function which will just derive two keys, one for authentication and one for confidentiality out of the master key. And so what we could expect from crypto library is to propose this kind of approach and only this kind of approach. So what could go wrong? You could use AES in ECB mode. You could use AES in CBC mode with a constant IV, with a random IV and without any authentication, which is bad. You could use AES in CBC mode with a random IV, with a hashMAC on the ciphertext, but using both the same key, which is bad. So there are many combinations that should be avoided in practice. And basically, can we put these kind of decisions on the developers' shoulders? Probably not. So if we come back to software and to crypto libraries, many of them allow the developers to use options that are insecure. For instance, secure ciphers without mode of operations. And the developers will invent a kind of mode of operation which most likely won't be secure. Or secure ciphers with insecure mode of operation, non-authenticated one, like AES-CB or just AES-CBC, or secure ciphers with a secure mode of operation but with insecure parameters like AES-GCM, GCM, but with repeating nonces. Using the same key for encryption and authentication when you are not using authenticated encryption modes. So a new time, there is a lot of, if you take at the combinatorial problem of giving one secure combination out of all the possible ones, then the likelihood to take the proper one is very, very low. So here is just a screen dump of the features of crypto libraries. And basically, okay, the first one here is proposing authenticated cipher modes, which is nice because developer taking one of them by chance is on the safe side, but also a lot of unauthenticated cipher modes. So my question is why? Why a developer which maybe has not a lot of knowledge about cryptographic security should be given without any hint to use AES ECB, for instance? This is a real question that one should ask. So here is the first requirement for my dream crypto library. Offer only higher level APIs implementing authenticated encryption, or if really you don't need any confidentiality, just sealing, so just applying a secure mark on the data. And if you, a crypto library would still like to offer a lot of features to its users, then it should force the developer that will compile it to build the library with, I don't know, with a flag which allows to export low-level APIs and warning at compilation time and in debug mode for every use of an insecure low-level API. Why? Because either the guy is knowing what he's doing, or he should have a doubt and maybe ask oneself if he has used the library cryptographic in the good way. An example of good practice is libsodium. Because it's here you have all the code necessary to encrypt, securely encrypt, or with no, it's just a Mac case here. To have just to seal data, so just to apply a Mac on some data. And you see that you have very few things to do. So you have a very high level API to do this that just take a message length, a key, and returns a MAC. And to verify, you just feed the same data and you get OK, not OK. So here there is very, very few mistakes that can be done. There is, no, not in that case. So this API is quite developer proof, meaning that if a developer, so no, it does not give the opportunity to the developer to do mistakes. And if you would like to encrypt additionally, then there is this secret box easy API that does everything, takes a message length, a key, a nonce, and here we can discuss about it later, and return a ciphertext. And when you open that secret, crypto box, then you don't have to do a lot of operation. You have a single API call, and either you get OK with a plain text, or you get nothing, just a not OK if the data have been manipulated. Okay, that's all for the security models. Now let's have a look at primitives, cryptographic primitives. So a new time here, I have the full list of one of the crypto libraries that I am discussing, and it offers a lot of features, a lot of capabilities. So we have already discussed about unauthenticated cipher modes, which are okay, maybe not so useful for a developer really looking for security. We have version of AES with constant time versions, but we have also non-constant time versions, so meaning insecure versions. Why? I'm just asking that. We have a lot of other ciphers that today are not very used. So all the AES finalists, Twofish, Mars, Cast, RC6, Serpent. So do you know a lot of applications which are using Mars or Serpent? Maybe TrueCrypt, but I don't know a lot of them. We have stream ciphers, including broken one like RC4. We have DES. DES is 40 years old. Come on, 60-bit key. DES X, it's an 80-bit version of DES. So who is using this and who is going to use this now today in 2016? We have other very, very exotic stuff, RC2, RC5. So that's all stuff which is either completely obsolete or partially broken. Who is here? Who does know about Lion? Who has ever heard about Lion? Nobody. Nobody. Okay, Lion is a very old design by, if I remember well, Ross Anderson and Biham, which dates back from the 90s. So it has a nice name. So maybe a developer will just be attracted by the name and use this old stuff. So I don't know. You have hash functions. Okay, SHA-1. SHA-1, everybody says you should avoid the SHA-1 because it's broken, but it's not broken, but it might be broken. Okay, maybe we are waiting for that collision now for almost 6 years. Well, I don't know. But who is going to use ripened 128 or Tiger, which is an old stuff? So MD2, which you can invert almost by a head, MD4, which is completely broken, MD5, DESMAC, and very obsolete algorithm. So if you ship a cryptographic library, is it really necessary to have this old stuff for your developers? I don't think. And even worse, you have non-cryptographic checksums. So they are quite cool. They are fast. A CRC much faster than HMAC. And they are pretty fast. So maybe I could replace my HMAC by a CRC. Maybe it's a good idea because I won't have such a performance problem. And I'm very lucky, so it is available in my cryptolib. So does a non-cryptographic checksum have to be in a cryptographic library? I don't know. Okay. This is not the case. If I remember well, it's a Botan library, but most other libraries offer such a high diversity of crypto. So by default, I am in the opinion that they should not be available without an effort from the developer at build time. So many crypto libraries, in summary, offer the option to use non-cryptographic algorithm, like your Mersenne Twisters, or PRNG, Adler, CRC32, insecure ciphers, DES, RC4, MD5, SHA-1, insecure variants of CBCMAC, which should be used only with fixed length data, insecure protocol, SSL2, SSL3, insecure cipher suites. For instance, one of my favorites is RSA with export key size with RC2 CBC, 40-bit and MD5. There is words with TLS 000, but this, when it is available, maybe somebody will use them. So if you would like to propose weak ciphers to your user, a crypto library developer should force the guys building them to build the library with a special flag to having access to those weak or obsolete ciphers. And a new time, if you want at compilation time in debug mode for every use of unsecure low-level API, maybe you will attract the attention of a developer. The concept of self-defending implementation in crypto code is also quite important. if you just look at this snippet of codes, who knows that, which kind of code is it, which kind of crypto library? No, it's Liptom Crypt. Who knows about Liptom Crypt? Okay, so Liptom Crypt was written by a teenager about 10 years ago, which was just passionate about cryptography. And he wrote a whole library himself at the age of 16 or 17, and he put it in the public domain. So at the end, this library had a lot of capabilities, and it was pretty fast. So he did a very good job at optimizing everything. Now, and we just forget about this library, and now it's in the wild, it's in the public domain. For instance, Apple is using Liptom Crypt for its common crypto implementation. So you find this kind of code in the Apple code base. And here, typically, what you can imagine is when you are computing a key schedule of tripledess, it is well known that tripledess was designed with back compatibility in mind. So it means that if you feed it with 3 times the same key, then you fall back on des with a 56 bits level of security. So when you compute a key schedule, usually it's done once, and then you will reuse the subkeys a lot of time to encrypt a lot of data. And you have some time that to check things such that you can, this time you can amortize on many encryption. So here, for instance, we could expect that this library, because it's computing a triple-des key schedule and not a single-des key schedule, just check that the 3 keys are not completely equal, because otherwise you don't have triple-des, you have single-des. Another example I like a lot, it happened about 2 years ago, in 2014. I was just looking for an example of bad implementation for my students for the exam, my industrial cryptography lecture. And it took me about 15 minutes to find one, and I found one in pcrypto, which is the most important crypto library for Python. And there is a counter mode API, so there is an object allowing to handle a counter and to handle the incrementation of a counter. And if you look at this API, then yeah, you see that it is very, very complicated. So for the pcrypto API, a counter is something with a prefix, with a counter, and with a postfix. Okay. Now the prefix or the postfix can have a length of 0, but they can also have a large length. And actually, if you look a bit deeper in the API, you see that there is a Boolean flag that is called allow wraparound. So it means that if you reach the end of the counter, so 2 to the n minus 1 when the counter is n bit, then you just wrap to 0 and you continue. So this is exactly what we don't want for a nonce, which should be a non-repeating number. Okay, and when I have, okay, so I was very happy. I've taken this in my exam and put it as my example. But I have also written a GitHub issue. So it was in November 2014, saying, okay, maybe I would remove this flag because it's not a very good idea to use this, because if you are using a ES encounter mode with a repeating nonce, then you will have some problem. This should be removed because it will help developers to write byte crypto. And then nothing until July 10. And the guys with my tenor and the developer of pcrypto said, I think you probably are right. Effectively, I have seen some problem with developers and this one, and this is a bad idea. We should remove it. This is one of those where the pcrypto specific options that doesn't exist in other libraries. So I would be probably wise to just drop it. It is still there, and nobody is using this until, or maybe maybe somebody will just use it once, and this will be bad. So if you write crypto code, you should only offer capabilities that are useful for developers and that do not allow him or her to trigger security-related mistakes. And this is a typical example where you have a very flexible API, which opens a lot of different choices to the developer. And if you have too many choices, then probably you will do a mistake. Okay, for the primitive, let's speak a bit about security parameters. And let's discuss a new time about self-defending implementation. So some ciphers are designed to have a flexible key lengths, not only 128, 192, and 256 bits like for the AES. But for instance, Blowfish, you can have a key between, if I remember well, between 32 bits and 2048 or something like that, which is completely insane for a symmetric key. RC5 is the same. So we could expect that the implementation emit a warning or even refuse to work to key schedule in standard condition when the key length is smaller than 80 bits, which is a very, very, very teeny security margin. And for instance, and you cannot find, you don't find in practice such self-defending implementations. Or the best example I have found is the GPG implementation of Blowfish, also in libjcrypt. It is pretty defensive. It does a self-test. So every time you schedule a key, there is a self-test so that the key schedule is working well. It looks for weak keys. A weak key is a key happening with a likelihood of 1/4 billion, I think, and which slightly weakens the cipher. So the implementation is looking for weak keys, but it allows 32-bit keys without saying anything. So if a developer is just key scheduling a key, a Blowfish key with a 32-bit keys, this will work pretty well. Most libraries don't tell anything when you generate an RSA key with a too short key length. We know today you really should have a minimal key length of 1024 bits for very short-term data, and better have a larger key like 2048 bit one. So let's have a bit of fun. This is not so old version of OpenSSL. And by default, it does quite a good job, because when you just ask OpenSSL to generate an RSA key, by default, it will generate a 2048-bit key. So this is quite good. But if you take the version of OpenSSL that was at the same time shipped by Apple, it was a bit different. Because by default, it generated a key with 512 bits, which you can break in a couple of days now, today, with a very, very low-cost hardware. But it's even worse. Do you like RSA 128-bit keys? That works. 64-bit RSA keys? That works as well. 32-bit RSA keys? That works. And then I was playing, and I say, okay, let's say 16-bit keys, RSA keys, and that doesn't work anymore. I was very disappointed. And actually, I have looked at the code, and what you can find is dedicated lines of code handling very, very, very small RSA keys. So you have a loop, because when you have very, very small RSA keys, then you don't have so much prime numbers at your disposal. So if you generate prime numbers at random, then you will have collisions between your prime numbers. And sometimes it does not work well. So OpenSSL will invest a lot of efforts to try to do a very small RSA keys, and after 3 times, or I don't know how many times, you will just say, okay, I cannot generate such a small key, I'm sorry. This is something that should completely disappear. So it's not only the problem of OpenSSL. The OpenBSD guys have said, okay, after Heartbleed, OpenSSL, that's a crap, it's full of bugs, we will just take it and improve it and apply our coding standards. Yeah, okay, but sorry, I can also generate 32-bit keys with LibreSSL. And if you say maybe Google, which most of the time do a pretty good job in terms of security, and they have effectively their own version of OpenSSL, which is called Boring SSL. It's a fork of OpenSSL that is designed to meet Google's needs. Unfortunately, Google also needs 32-bit RSA keys. Okay. If you look at other libraries, libgcrypt, you see that there is somewhere there is a check, but only in FIPS mode. So what is FIPS mode for libgcrypt, and when is it triggered? I don't think it is triggered in most situations. Botan in 2015 also had a check, and a check was fixed as 512-bit keys, but things improved because last week it was set, so the very latest version of Botan, it was fixed to 1024. So you see that things move a bit, but not for every crypto library. Another example of Google code here, you see that there is a strict check on the key size and HMAC sizes and RSA sizes, and if you don't if you are not in the proper interval, then you won't be able to generate a key, which is a kind of good practice in my opinion. Okay, but there is not only RSA. You can also define very unsecure Diffie-Hellman groups, which can be broken in seconds. You can generate or use weak elliptic curves that offer only 64-bit of security. You can use weak cipher suites. So actually, in most crypto libraries, you can really do a bad job if you would like. So for a Dream crypto library, it should offer only security parameters and configuration options that are meaningful in terms of security. If you would like to have, I don't know, a CTF problem involving RSA 128-bit keys, fine, okay, but I will compile my crypto library in a certain mode that allows me to generate 128-bit RSA keys. If it should offer on safe security parameters by default. So if you don't input a length or a key length or something like that, then it should output something secure, like the latest version of OpenSSL, but not the Apple one. And a new time, if really you require weaker or obsolete variants, then you should ask for an effort of the developer, ask for something more than just using the standard API and standard compilation options. Now, let's have a look at cryptographic parameters. So, basically, without secure randomness, today you cannot do crypto. Okay? We know that we need randomness. So if you don't have a secure pseudo-random number generator, don't even think about beginning to design a solution relying on cryptographic security. We know that this is quite difficult to have a properly seeded, cryptographically secure pseudo-random generator, but to do crypto in any way, you must have one. So most cryptographic libraries today do a rather good job in providing a cryptographically secure PRNG or by interfacing it to the one of the system. But one problem that you can see is that most crypto libraries put the responsibility to use the CPRNG on the developer's shoulders. So here, two bad things can happen. Either to forget to use random values, to have static parameters, or use a non-cryptographic PRNG, which is quite common also. And even if the documentation of some crypto libraries, it's Crypto++ here, they just give an example of what not to do. It's saying, okay, we show you what is bad to do, but don't use it. And everybody knows that developers don't copy-paste code from the web into their code. So, well, it's a bit bad practice.
And this is where I come back to the user to the lipsodium case. Uh, Effectively, authenticated encryption needs not random values, but it needs something apparently easier or something weaker in terms of requirement. It requires something which is non-repeating a nonce. But actually, today, the best way to generate a nonce is to generate it randomly, unfortunately. So putting the generation of the nonce on the user's shoulders is a bit dangerous. And they say it, the nonce doesn't have to be confidential, but it should never ever be reused with the same key. So the easiest way to generate a nonce is to use random buff. So why is it left to the developer here and not put outside the API? So situation where you have you have really a nonce at your disposal. There are very few in practice. You have, for instance, disk encryption, but it's not when you can use a sector of other nonce. But most of the time, you don't have a guaranteed non-repeated number at your disposal. So just generate it at random, and then you will be safe if the nonce is sufficiently large. And the API should handle it itself. And it is such a problem that even the academic community has triggered a new research direction, which is nonce misuse resistant encryption. And we have security models, and we have algorithms that, okay, that normally you should not use repeating nonce, but here, if you are using my algorithm and you repeat the nonces, then, okay, it's not that bad, okay? This is something that one should ask, why don't you generate your nonces just at random, and you will be safe, that's it. It is in the public key, it is well known that ECDSA signatures also uses nonces. We have well documented cases where when you fail to do, when you repeat a nonce, then something bad happens, you just lose your private key. This is quite bad, and so you can ask Sony for that. So some algorithm now, there is also an RFC with ECDSA. Some algorithm now just deterministically generate a nonce out of the message, which means that you will have on the same message two times the same signature, but you will guarantee to have a non-repeating value, at least probabilistically. And actually, in the APIs with ECDSA, we also already have this danger which has been recognized, and the nonce is really generated by the API, and it's not left to the developer. So here we are in a pretty better shape. So in encryption mode, the IVs and nonces should, whenever possible, be generated in a transparent way and written by the API. We must assume that we have a CPRNG, but if you don't have a CPRNG, don't do crypto. And a new time, a bit about, just to finish, about API simplicity. This is the code that you need to encrypt some data with OpenSSL. That's pretty simple, right? I love it. At least 30 or 40 lines of code, at least 10 different API calls, such that at the end you just manage to encrypt something. If you take the lipsodium case, you will see that there is a single API call. Simplicity with error handling. We know today that cryptography is very sensitive to the handling of errors. Everybody has heard about padding oracle and this kind of stuff. Just take high-level APIs of OpenSSL. So OpenSSL with verify. So you should receive something which is signature okay or signature not okay. Basically here, ECDSA verify, we just return a 1 for a valid signature, a 0 for an invalid signature. So here, everybody may just begin to think, okay, that's not the usual way to do. And a -1 when there is an error. So somebody writing, if ECDSA verify, blah, 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 And he's assuming that there is a good signature. He's completely wrong, because maybe it's a good signature, or maybe something, an error was triggered. Here, with lip sodium, we have only a single case, two cases. It's signature okay or signature not okay, and there is no more information about what the signature was wrong, or something like that. If you look at the RSA code, you will see that the code will return you 68 different error cases, and if you protocol those, if you your developer will handle this case, most likely will introduce oracles, and the shape of its cryptographic code will be bad. So in debug mode, a crypto library could possibly return detailed error message, because we have to debug, we have to assume information. But in production mode, a crypto library should just return a Boolean flag. Okay, I was able to verify, not okay, the signature is wrong, or something nasty happened. Okay, I was able to decrypt, or the ciphertext was valid. Not okay, I don't know, but it's not valid, so don't use it. And API and error handling should be as simple as possible, of course, which is not the case. I arrive at the end of my talk. So crypto libraries should stop immediately assuming that their crypto users are omniscient cryptographers. All of them are not omniscient cryptographers. And by the way, omniscient cryptographers do not exist anymore. Maybe it was the case in the 80s, but now cryptography has gone so complicated that it's not possible to know everything about crypto. A non-secure functionality should be killed, or must be killed. Crypto libraries, whenever possible, should stop put security-related responsibilities on developers' shoulders. Crypto libraries should refuse to generate too small keys, too small cryptographic groups, which do not have any meaning with what regards crypto. And they should refuse to use weak or obsolete cryptographic configurations, or ciphers. And last, no, not last one. Whenever possible, crypto libraries should generate themselves the required initialization vector, nonces, or if it's possible, if it's not the case always, but also the session keys and symmetric keys. And last but not least, I think that the screen here is too small. Crypto libraries must be extremely simple to use, and now most of them are extremely complicated to use. So this is the conclusion of my talk. Perfect crypto library does not exist yet. There are better ones. Lipsodium is an example. Even if a few of them converge in the good direction, but still, when you are using a crypto library, just assume that you are not very safe in terms of security. That's it. I don't know if you have any question. No questions. So don't use crypto library anymore, and you will be safe. Thank you.